Limiting reagent calculations. We finally made it. This is the last lesson in a whole chapter on stoichiometry. And most students, when they think of stoichiometry after they've completed a year of chemistry, it is usually this particular aspect of it they are thinking of. And usually it's not a pleasant memory associated with it. So that's not going to be the case for you, because by the end of this lesson, you're going to have a very good handle on performing these lovely calculations. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. And in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. You can find our premium courses on chadsprep.com. Now, this lesson's part of my new general chemistry playlist, and I'm putting up several lessons a week throughout the school year. So if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. So let's dive in here. And we need a chemical reaction to talk about in the context of limiting reactant calculations here. And the one I've chosen is the production of ammonia from nitrogen gas and hydrogen gas. And here, 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to produce 2 moles of ammonia gas. And that's the reaction we're going to look at here. And my first question for you, if you were sitting here live with me, would be, how many moles of N2 gas do I have? That is the question. Yes, you. I'm asking you. How many moles of N2 gas do I have? Cool. Now think about your answer. Now my next question is, how many moles of H2 gas do I have? Okay, now think about that answer. And my next question for you is, how much money is in my wallet? And hopefully on that last one, your answer was, I don't know. And the key here is that actually that should have been the answer to all 3 of those questions. How much N2 gas do I have? I don't know if you've been to my house. Do I have like nitrogen gas tanks sitting on the side of my house or hydrogen gas tanks sitting on the side of my house? And so you should have said, I don't know. And the key is this, and the big point I'm trying to make, I'm being a little bit, tongue-in-cheek here, but the big point I'm trying to make is that a balanced chemical reaction never tells you what you have. It never tells you what you have. It is only going to tell you the mole-to-mole ratio in which things react. So in this case, it says that 1 mole of N2 gas reacts with 3 moles of H2 gas to produce 2 moles of NH3 gas. It's a 1:3:2 ratio, and that is all it tells us. So how much we actually have of either of these reactants or products is something that's extraneous that has to be given. So if I told you that I actually do have 1 mole of N2 gas, I might say, well, how many moles of hydrogen gas do I need to react with it? Well, based on the 1:3 ratio, I would need 3. What if I said I have 2 moles of N2 gas? Well, then how many moles of H2 gas would I need for it to react with? Well, we'd say 6, because that 2:6 ratios reduces down to that 1:3 ratio. And so again, your coefficients here ultimately are only going to give you a new way of finding mole-to-mole ratios, a 1:3 ratio if you're comparing N2 to H2. Or if you're comparing N2 to NH3, it'd be a 1:2 ratio. Or if you're comparing H2 to NH3, it'd be a 3:2 ratio. So you can compare any 2 species out of the reactants and products and get a mole-to-mole ratio out of that. And so earlier in the chapter, we found out that you can get a mole-to-mole ratio from a chemical formula. Well, now, and I hinted towards it at the time, you can also get it from the coefficients in a balanced chemical reaction. But again, it just tells you the ratios in which things react. It never tells you what you actually have. That has to be extra information that is provided. And so now I'm going to tell you. So if you've got the study guide in front of you, I'm telling you that to look there. But we've got 6 moles of nitrogen gas. And my first question is, how many moles of H2 gas would I need for that 6 moles to react completely? And again, the key is based on that 1:3 ratio, and you can probably do this in your head. And we're going to do the first few calculations here with numbers that are nice and pretty and things that you might be able to do in your head. In fact, we'll do most of the lesson with stuff that you may be able to avoid using a calculator for. But be prepared. You need to learn this process down pretty good, because you are going to get problems on your homework and your exams that will definitely require you to use a calculator. But if we do this with problems without the need for a calculator, it'll make learning the process that much easier. All right, so with 6 moles of N2, how many moles of H2? And again, based on that 1:3 ratio, I can see it's 3 times more moles of H2, and 3 times more moles would be 18 moles of H2, and that's the answer to this question. Now, if we look at how we work this out, what we're going to use here is a mole-to-mole ratio, and we're going to put the moles of N2 in the denominator, so they'll cancel, and we'll put the moles of H2 in the numerator, and for this mole-to-mole ratio, the numbers are just the coefficients in the balanced reaction. So coefficient for H2 is a 3, and the coefficient for N2 is an implied 1, and so dimensional analysis gets those moles of N2 to cancel, and 6 times 3 over 1 is indeed 18 moles of H2. So if I want that 6 moles of N2 gas to react completely, I would need 18 moles of H2. Now, next question, we're going to start with that 6 moles of N2 yet again. And this time the question is different. Instead of worrying about how much H2 I need for it to react with, the question is what is the maximum number of moles of NH3 that can be produced? And so in this case, I'm relating the moles of N2 to the moles of NH3, and it's a 1-to-2 ratio. And so in this case, based on that 1-to-2 ratio, you can probably see like, well, I just get, the maximum I get is twice as much, and twice as much would be 12 moles. And that's exactly right. So, and again, the process though, with the dimensional analysis here, we'll put moles of N2 in the denominator, we'll put moles of NH3 in the numerator. We've got a mole to mole ratio here, and again, that mole to mole ratio is just going to come from the coefficients of these two species in the balanced reaction. We get 2 moles of NH3 for every 1 mole of N2 according to those coefficients. Dimensional analysis, those units will cancel, and 6 times 2 over 1 is indeed 12 moles of NH3. All right, so this is not so bad as long as we're dealing with it entirely at the level of moles. Whether you start with a number of moles of a reactant, or you're trying to get so many moles of a product, or find out how many moles of the other reactants you need, if we stay in the land of exclusively of moles, life is good. It's not so bad, and we've got multiple ratios and life is good. The problem comes with, what if we start in the land of grams instead? And so instead of telling you that I got 6 moles of N2, what if I told you that I've got 56 grams of N2 instead? And now my question's the same though. How many moles of H2 do I need for it to react completely? Well, back when we had 6 moles of N2, when I knew the moles of N2, I just used that 3-to-1 ratio to figure out that I needed 18 moles of H2. And as long as we knew the moles of N2, I just multiplied by that 3-to-1 ratio regardless. So if this had been 6 moles or 10 moles or a million moles or 0.437 moles or whatever, I would have multiplied by a 3-to-1 ratio to get there. And so the key is, if you don't know the moles, well, then you can't use the mole-to-mole ratio. And so if you're given the grams instead, first thing you need to do is convert it to moles, because then you can take advantage of those mole-to-mole ratios. And in this case, how do we convert grams to moles? Well, we'll put grams of N2 in the denominator, we'll put moles of N2 in the numerator, and that connection, if you recall, between moles and grams is always, always, always the molar mass. And so if you look at the periodic table, nitrogen has a molar mass, a single nitrogen atom, of 14 grams per mole, but for N2, it's diatomic. You got to factor that in, and so it's going to be 28. And so 1 mole weighs 28 grams. The grams will cancel, and 56 divided by 28, I chose this to be nice. So in fact, 56 divided by 28 is indeed exactly 2 moles, but let's not stop there. And, let's not break this up into multiple calculations. We'll then take this a step further, and we can now convert it to moles of H2. We'll divide by moles of N2. That's our mole-to-mole ratio. And again, that comes from the coefficients. We get 3 moles of H2 that are required for every 1 mole of N2 we use up as well. And now 56 divided by 20 is 2 moles of N2 times that 3-to-1 ratio means we need 6 moles of hydrogen for it to react completely. Now let's just pretend this question had not asked about the number of moles of H2, but let's say it had taken it a step further and it wanted the number of grams of H2. Well, if we wanted the grams of H2, well, then we just need to convert moles to grams at the end. And we could have done that. We could do that now, but we could have done that as part of the process here. And we're going to go back and do that. This was the answer to that question, but had I been asked for the number of grams, we would have just taken this an extra step. And to convert from moles of H2 to grams of H2, again, the connection between moles and grams is always the molar mass. And a single hydrogen atom has a molar mass of 1 gram per mole, but we have H2 diatomic, and so it's going to be 1 mole weighs 2 grams. And so in this case, we'd get, again, 56 divided by 28 was 2, times 3 is 6 moles, and times 2 gets us 12 grams of H2. This is often, when you take it this far, when you start with grams and you end with grams, so this is often what we refer to as your grams, 2 moles, 2 grams type calculation. So commonly you hear that grams to moles to moles to grams. And grams to moles and moles to grams, that's always a connection through the molar mass of whatever chemical species you're talking about. But it's the connection between moles, and that is where you're required to use a mole-to-mole ratio. And in this case, again, we're getting that from the coefficients in the balanced reaction. So now we're going to get into limiting reagent calculations a little more proper here, and I'm going to come up with a mock fake chemical reaction here that's not really chemical in nature at all, but one frame plus two tires can make one standard bicycle here. That's what we're going to deal with. And so if I look at the ratio of frame to tires, it's a 1-to-2 ratio. If I look at the ratio of frames to bicycles, it's a 1-to-1 ratio, or tires to bicycle, it's a 2-to-1 ratio. And we're going to do what's now called a proper limiting reactant calculation here using this example because it's something that you can see. Once we start doing this with compounds and molecules and atoms, it gets a little bit vague in students' minds and they can't picture it. But we'll do it with something we can picture first. So let's say that I gave you 10 frames. 10 frames. And my question would be, you got 10 bicycle frames, what number of tires do you need to use up all your frames? Well, based on the 1-to-2 ratio, you would need 20 tires. And I'm guessing there's a really good chance you're not struggling to figure this out. And my next question is, if I give you 10 frames, what is the greatest number of bicycles, complete bicycles, that you could make? Well, 10. It's based on a 1-to-1 ratio. For every frame, you can make no more than one bicycle, so 10 frames can make 10 bicycles. So what if I gave you 10 frames and then I gave you 22 tires? And the question is, how many bicycles can you make maximum? What's the greatest number of complete bicycles you can make? And so there's a couple different ways to figure this out. And we have to talk about what's called the limiting reactant or limiting reagent. And it's whichever one of these limits the greatest number of bicycles we can make. So whichever one's going to run out first, we might say. And so in this case, again, you're probably not struggling to see this. You're probably just looking at this and be like, Chad, you can make 10 bicycles. Okay. And I want it to be that intuitive for you because once we start applying this to a chemical reaction and stuff like that, it's going to get a little more, a little harder to see, so to speak. So in this case, the way I want you to approach this, and there's multiple different ways to figure this out. You could look at this and say, well, 10 frames needs 20 tires. Since I have more than 20 tires, then the 10 frames is the limiting reactant. I have more than enough tires for all 10 frames to react. And you can totally do that. It's just not the approach I'm going to take. What I'm going to do is figure out how many bicycles I can make based on using up all the frames and then separately based on using up all of the tires. And whichever one leads to a lower number of bicycles, a lower number of product in this case, that's the limiting reagent. So in this case, 10 frames based on the 1-to-1 ratio can make me 10 bicycles maximum. But 22 tires based on the 2-to-1 ratio can make me half as many, or 11 bicycles. So we have enough frames to make 10 bicycles, we have enough tires to make 11. Well, then we can only make 10 bicycles. You're gonna run out of frames before you've used up all your tires. So we would call the frames the limiting reactant or limiting reagent. We call the tires the reagent in excess. And the fact that we can make a maximum of 10 bicycles, we'd refer to that 10 bicycles as the theoretical yield of our product in this case. So that's kind of the idea here. And again, I'm not even working this out proper. We'll work this out proper in a little bit with a real chemical reaction, but I wanted to use an example that you can see and with numbers that are nice and things of this sort. But that's kind of the approach we're going to take. And so let's see how this applies to an actual chemical reaction here. So now we're going to do a limiting reactant calculation proper, or at least a set of calculations. And in this question, we're going to be given 112 grams of N2 and 30.0 grams of H2, and they are going to react completely. And we've got 3 questions to answer. And the first question is, what is the limiting reactant or limiting reagent? Same diff. Second question is, how much NH3 is formed if these do react completely? And then the last question is going to be, how much of the reagent in excess is left over? All right, so the first question is, what is the limiting reactant? And really, that's going to be the one that runs out first. Now, there's a temptation here to look and be like, well, I've got 112 grams of N2 and only 30 grams of H2, so obviously I have way less H2. But you can't look at it that way. And so one, these are given in grams, so not moles. And I know that, it's a 1-to-3 ratio in moles. I don't know what the ratio is in grams. And so first of all, it's not even a 1-to-1 ratio, it's a 1-to-3 ratio. And again, that's a ratio of moles, not a ratio of grams. And so don't yield to the temptation that just says pick whichever one you have less of, because that's not usually true. Randomly it could be either one, but a good instructor is going to write a question in such a way that if you just go with the easy temptation here to pick whichever one you have less of as the limiting reactant, it's probably going to be wrong. So just word to the wise. All right, so what we need to do is figure out how much NH3 we can make maximum if either one of these runs out. And again, whichever one leads to less is going to be the limiting reactant. It's kind of like if I was into construction and I have enough bricks to make 1,000 homes. I build homes, let's say. So I have enough bricks to make 1,000 homes, but I have enough drywall to make 3 homes. So can I make 1,000 homes or can I make 3 homes? Well, obviously with the supplies that I have on hand, I can only make 3 homes and I'm out of drywall. Drywall would be the limiting reactant in that case, and the bricks would be the reagent or reactant in excess. So that's kind of how that works. So we're going to figure out how much NH3 we can make, assuming either one of these runs out completely, and whichever one makes less is the limiting reactant. All right, so in first thing, we're going to convert this to moles. I can relate the moles of N2 to NH3 based on this 1 mole to 2 mole ratio, but I've got to have moles. And so first thing I'm going to do is just turn this into moles. And so in this case, 1 mole of N2 weighs 28 grams. Again, it's diatomic. And now that I've got the moles of N2 here, we can then convert that into the moles of ammonia, NH3, from N2, and that's that mole to mole ratio, which in this case is just the coefficients in the balanced reaction. So that's a 2-to-1 ratio. And we'll go from there. So 112 divided by 28 is exactly 4, it turns out, and 4 times 2 over 1 is 8. And so if all of our N2 reacts completely, we would get 8 moles of NH3. Now, hydrogen's going to be a little easier on the math here, but again, we've got to convert this to moles first. So, and again, that's through molar mass. 1 mole of H2 weighs 2 grams. And so 30 grams is going to end up being 15 moles. So, and we can kind of see that we've got a 3-to-2 mole to mole ratio. We'll put moles of H2 in the denominator, moles of NH3 in the numerator. And again, it's just the coefficients right out of the balanced reaction. So 2 moles to 3 mole ratio. And so in this case, 30 divided by 2 is 15, and 15 divided by 2/3, or say 15 multiplied by 2 over 3, multiplied by 2/3, is equal to 10 moles of NH3. And so you're supposed to take this now, that you have enough N2 to make 8 moles of NH3. You've got enough H2 to make 10 moles. So can you make 8 moles or can you make 10 moles? Well, you can only make 8 moles. That's kind of the idea here. And we call this 8 moles here the theoretical yield. It is the maximum number of moles of NH3 we could possibly make. And the reason we call it the theoretical yield is because usually you don't make the maximum. It turns out that for most chemical reactions, there are certain side reactions that are sometimes possible. And so some of the reactions get used up in making these other side products and not making the product of interest. So you never end up getting this maximum. We'll also find out that most reactions don't go to completion, but you'll find that out in your second semester. And so, but it just turns out this is, we call the theoretical yield because theoretically this is the most you could ever get, even though in practice we usually don't even get this much. All right, so there's our theoretical yield of 8 moles. We're never going to have any chance of getting 10 moles. We just don't have enough N2 to get there. And so now we've answered 2 questions. Our limiting reagent here, or limiting reactant, same diff, is N2. Our theoretical yield here is going to be this 8 moles of NH3. So in this methodology, we've actually solved for both at the same time. Now, if you were doing this as a multiple choice test question, and if they asked you, what's the theoretical yield? Or as I asked it, what is the greatest number of moles of NH3 that could be formed or produced or something like this? They could ask this in moles or grams. And had we asked this in grams, had all the answer choices in a multiple choice question been in grams, you would have had to taken this one step further. And you'd had to figure out that the molar mass of NH3 is 17, 14 plus 1 each for those 3 hydrogens, so 14 plus 3 is 17 grams per mole, and you would have multiplied 8 times 17, which would have given you like 136 grams of NH3. So, but I'm going to stop there. That was sufficient for what I was asking. And the next question, though, is the last one here in the assignment, and it's the most challenging one for students. And the question is, how much of the reagent in excess is left over? And that could be how many moles or how many grams, and we'll do both. And in this case, we can see that the H2 is the reagent in excess. And the question though is how much is left over? And when you're going to figure this out, you want to start from a theoretical yield you just calculated. So, and the idea is that you know how much of this H2 that you have, that you've started with. The question is how much actually gets used up in making your theoretical yield of your product. And then we'll just subtract that off from how much we started with. So we're going to start with that theoretical yield of 8 moles NH3. And then I want to find out how much of the H2 got used up. So we'll relate the moles of NH3 to the moles of H2, and that mole-to-mole ratio, once again, comes from the coefficient, so 3 moles of H2 for every 2 moles of NH3. And we'll take this one step further and go to grams here. And again, that connection between moles of H2 and grams of H2 is always the molar mass. And 1 mole of H2 weighs 2 grams. And then 8 times 3 halves. And then this 2 will cancel right here. So 8 times 3 effectively is 24 grams of H2. And this is how much is going to be used or consumed. And so we started with 30 grams. We just figured out that to get our theoretical yield of 8 moles of ammonia, that 24 of those grams are going to get used up. And so we'll just subtract that off. And we'll see that we've got 6. And to get 3 sig figs, we'll make it 6.00 grams of H2 either left over or in excess is the way we might say that. Cool. And the big mistake that a lot of students make is they'll sometimes figure out that they need to start with this theoretical yield, but then they think that they just calculate directly to here when, again, they're going to take the original amount of the reagent in excess they started with and subtract off how much actually was used that we calculated here to get that difference. And it's that difference that is the amount that's left over. All right, so we've got one last little calculation to do, and that is a percent yield calculation. And turns out your percent yield is equal to what's referred to as your actual yield, how much product you actually got, divided by your theoretical yield times 100. And if you recall, we said that your theoretical yield is theoretical in the sense that, you might have some side reactions happening that use up some of your reactants, and so not all your reactants end up going to make products. And that most chemical reactions don't actually go to completion. So for a lot of times, you'll end up with leftover reactants and not making as much product as you did. And so that's why it's convenient to talk about this actual yield, how much you actually got. And again, it should be less than your theoretical yield. If, for a lot of organic chemistry students, they'll end up with an actual yield that's bigger than their theoretical yield and end up with a percent yield that's over 100%. And usually that's a dead giveaway that your product is wet and you need to dry it off better because you shouldn't be able to get more than a 100% yield. So that's kind of the idea here. So this is our last calculation, and you can treat this as kind of being an equation with 3 variables. There's percent yield, actual yield, theoretical yield, and if you give, if you're given 2 of the 3, you can solve for the third. And so what we're going to do is we're going to take the problem we just did, where we got a theoretical yield of 8 moles, and if you recall, we hinted that that theoretical yield, if we calculated it to grams by multiplying by the molar mass, it would be 136 grams, and here I've written it out explicitly. And so we want to now say, last question on the sheet there is, if we actually only get 102 grams of ammonia as product, then what is the percent yield? So again, theoretically, we see that we could get 136 grams maximum. Well, we only got 102 grams. So what percent yield is that? And you can kind of think of this like, let's say I gave you enough money to go buy 10 pizzas and you only come back with 8 pizzas. And I'm like, where's the other 2 pizzas? And you just pocketed the cash or something. So you only came back with 80% of what I sent you out for. That's a 80% yield, 8 out of 10 possible pizzas. So kind of the way it works here. So with this theoretical yield calculation, we'll take our actual yield, again, given in this question as 102 grams, divided by your theoretical yield, and which is 136 grams, and then multiply by 100, and it turns out this comes out to exactly 75%. There's your percent yield in this calculation. And you can do this in grams or moles. I just decided to write it in grams because that's most likely how you're going to see it. But instead of giving you the 102 grams, I could have just said, hey, you only came back and actually produced 6 moles of NH3. Well, 6 moles out of a theoretical yield of 8, 6 over 8 times 100 would have given you that same 75% number. If you found this lesson helpful, a like and a share. Make sure YouTube shares this lesson with other students as well. And if you're looking for practice problems on stoichiometry and limiting reactant calculations, check out my general chemistry master course at chadsprep.com. I'll leave a link specifically to the course in the description. A free trial is available. Happy studying.